Welcome to Physics with Joe. In my previous video, I talked all about ray tracing for concave mirrors. If you haven't gotten a chance to watch that yet, please do that first. I'll put a link in the description below. Today, I'm going to focus on ray tracing for convex mirrors. I'll quickly review what ray tracing is and one of the key differences between concave and convex mirrors. Then we'll go through the 4 principal rays you use for ray tracing for convex mirrors. And finally, we'll talk about the only kind of image that a convex mirror can produce. So without further ado, let's jump right into it. As a reminder, ray tracing is just a graphical method of determining the location, size, orientation, and type of image produced by a spherical mirror, either concave or convex. A few important concepts that you need to know for doing ray tracing are focal point and focal length, center of curvature and radius of curvature, and then finally the central axis. As a reminder, the central axis is just a horizontal line drawn passing through the focal point, the center of curvature, and the middle of the mirror. For a concave mirror, the focal point was the single point through which all parallel light rays will cross after reflecting from the concave mirror. Now, a convex mirror is a little bit different. For a convex mirror, parallel light rays will never meet at a single point after reflecting. They actually diverge from the convex mirror. However, parallel light rays after reflecting from a convex mirror will all appear as if they originated from a single point behind the convex mirror. That is the focal point for a convex mirror. We sometimes refer to it as a virtual focus or virtual focal point because the light rays are not really emanating from that point. They just look as if they did. The center of curvature for a convex mirror is the center of a sphere of which it looks like the convex mirror is a section. All spherical mirrors, concave or convex mirrors, can be considered to be a part of a sphere. And the center of the sphere of which that mirror is a section is called the center of curvature. The distance between the center of curvature and the mirror is called the radius of curvature, and the distance between the focal point and the mirror is called the focal length. For a convex mirror, the focal length will always be 1/2 the radius of curvature, which means that the focal point is half the distance away from the mirror as the center of curvature. Or the center of curvature is twice as far from the mirror as the focal point. The way you do ray tracing is you always start by drawing the central axis, your mirror, the focal point, and the center of curvature. Now, if you were trying to get a mathematical answer, you would need to use a ruler and some kind of scaling factor and draw everything the exact right distance away. However, we usually use ray tracing as just a quick little check to see whether or not our answer seems reasonable. So you don't need to break out a ruler, you just need to draw things to the approximate correct distances. When doing ray tracing, we always draw the object as an arrow, regardless of what the object really is. And then we draw the principal rays starting from the tip of the arrow. And what we're looking for is where do these rays intersect after reflecting from the mirror? Or in the case of a diverging or convex mirror, where do these rays look like they originated from after reflecting from the convex mirror? So let's take a look at the 4 principal rays used for convex mirrors. Ray 1, a ray originally parallel to the central axis after reflection appears to have originated from the focal point behind the convex mirror. Ray 2, a ray heading towards the focal point after hitting the convex mirror will be reflected parallel to the central axis. Rays 3 and 4 are exactly the same as those for a concave mirror. Ray 3 is a ray traveling through a line that passes through the center of curvature, will reflect back upon itself after hitting the convex mirror. And then ray 4 is a ray striking the center of the convex mirror, will reflect at an equal angle on the opposite side of the central axis. Let's now take a look at ray tracing in action for a convex mirror. In this simulation, I've got my convex mirror, I've got my central axis, I've got my focal point, which is located 5 centimeters behind the mirror, which means my center of curvature is going to be 10 centimeters behind the mirror. Keep in mind that if we wanted to get a mathematical answer using ray tracing, I'd have to break out a ruler, draw everything to scale, but we're just trying to get the general characteristics of the image produced by a convex mirror. Again, no matter what the object is, you're always going to draw the object as an arrow, and then you're going to draw the 4 principal rays starting from the tip of the arrow. Remember, ray 1 is a ray initially parallel to the central axis. After reflecting from the mirror, looks as if it originated from the focal point behind the mirror. Ray 2 is kind of like the opposite. A ray heading towards the focal point behind the mirror, after reflection, is going to reflect parallel to the central axis. Ray 3 is exactly the same as for a concave mirror. A ray traveling along a line which passes through the center of curvature is going to reflect back upon itself. And finally, ray 4, a ray that hits the center of the mirror, is going to reflect at an equal angle on the opposite side of the central axis. And then what you're looking for is, where do these rays all look like they originated from after reflection? Now, for a concave mirror, after reflection, you can get all of the rays meeting at a given point, producing a real image. But what we'll see for a convex mirror, let's just play them all, is after reflection, none of these rays are intersecting. I do not have a real image. But if I look at the reflected rays and trace them all back, the point where it looks like they originated from, right here, that is the image location. And for a convex mirror, no matter where the object is in front of the mirror, notice that I'm always going to get my image being behind the mirror. And for a convex mirror, it's always going to be a virtual image, which is going to be reduced in size and upright relative to the object. That is the only kind of image that a convex mirror can produce. It doesn't matter where I am in front of the mirror. The image is always going to be behind the mirror, and it's always going to be between the mirror and the focal point. So in summary, we can use ray tracing to show that for a convex mirror, there's only one possible kind of image it can produce. A convex mirror will always produce a virtual, upright, reduced image no matter where the object is in front of the mirror. So, unlike a concave mirror, which can produce either a real or virtual image, which could be enlarged or reduced, only one kind of image produced by a convex mirror. That is a virtual image, which is behind the mirror, and that virtual image will always be reduced in size and upright relative to the object. Well, that is it for ray tracing for convex mirrors. Thank you so much for joining me. My name is Joe McCullough, and in my next video, I'm going to be talking about something super cool. So stay tuned.